say the least. You know, when I sent that email and said the first test was hard, I wasn't being honest. I sort of just said that to get you guys to study really hard. I didn't expect it to be hard, but apparently it was for some of you. And most of the problems they have nothing to do with 392 at all, actually. It's things before that, Calc 3, Calc 2, and all that stuff. So I'm just going to go through some of the most glaring problems that I found with this. I'm very upset and sad when grading these, but I'll try to maintain my composure when I talk about these mistakes. And just know that if I come off a little bit too harsh, it comes from a place of concern. But sometimes concern has to be conveyed in harsh language. Okay, and you'll see why I say that when we go through some of these mistakes. So let's start with problem 1. You don't even have to write down anything I'm writing down because they should be obvious, really. So yeah, problem 1, a lot of people missed it completely. A lot of people took the z values that I gave you as the radius values. Right, so I said, for example, on test 1, I said, between the planes z equals 1 and z equals 5, a lot of people made r equals 1 and r equals 5 when they're setting up a double integral. For which reason, I don't know why. I had some people giving me triple integrals to compute area. I had some people just not knowing how to integrate. It was a substitution problem when you set the thing up. Okay. But so far, those are okay. All right, those aren't so bad. The mistakes get worse. You move on to part B in problem 1 and C in problem 1, and you start realizing that things get really scary. You start realizing that people do not know the general forms. All right? So if you look in part C, for example, people do not know what the equation of a line looks like. It's not just that they don't know what the equation of a line looks like, it's a really big misconception, right? So I mean, if you're in algebra class, Math 190, you learn that a line looks like this. Right? That's the equation of a line. By the way, if I ask you for the equation of a line and you only give me the part without the equal sign, like mx plus b, that's not an equation, right? I mean, I let it slide this time. For people who actually gave me the right expression but didn't put the equation, I let it slide. But in general, if I ask you for an equation, it should have an equal sign. But that's not even the problem that I have, okay? So you know that here, this is like a line, right? So you know, for example, like y equals minus 2x plus 7, right? It looks like that, right? Y equals, I don't know, 3x minus 1, looks like that, okay? So you learn in algebra, that's what a line looks like. That's the form. It's a constant times x plus a constant. That's a line. Is this guy a line? The answer is yes, because it's a constant times x plus a constant. This is a line also. It's a constant times x plus a constant. Now, if someone taught you that that's what a line looks like, if it's not like that, it's not a line, and someone says, you know what? That's a straight line. At this point, it's not even about being mathematically talented. It's just about one of these things is not like the others. That's what it boils down to, right? It's looking at the pattern of what the formula should look like. You should know that if it does look like a constant times something plus a constant, it's not a line. Lines in 3 space are exactly the same thing. In a vector function, all your components are linear. Each component in a vector function for a straight line should look like that. A constant times a variable plus a constant. I had people telling me some things like, similar to this, but probably not the same thing. You know what, Jhevon? That's the tangent line, with a sine and an e to the t in it. Obviously, it's not a tangent line. Just as obvious as this isn't a straight line, which I don't even have to know what sine is, right? I pretend I didn't even learn trig at this point. I could simply match up the pattern to what I know a line should look like to this guy. They're obviously not the same thing. Apples and oranges, circles and squares. I can tell you this is what a circle looks like. If I show you a picture of a square and say that's a circle, you should be able to say, no, that's not a circle. You just told me a circle looks like this, and that doesn't look like that. You do not have to be mathematical. You don't have to any mathematical ability. You should just know that's what a line looks like, and anything else is not a line. The mere fact that people actually wrote things like that down as the answer was ridiculous. It has a trig function and an exponential in it. It's not a straight line. Just as how it's obvious that this is not a straight line. Right? Match up the patterns. Okay? That's the first thing. Second of all, this was another egregious mistake because the argument that kids usually have is that, it's been a long time since I took Calc 3, I took it years ago, blah, blah, blah. That mistake actually doesn't apply here because since this semester, in 2 quizzes, I asked you to write down the formula for a line. If you missed it on the first quiz, shame on you. I put exactly the same question on the second quiz, which you should have been able to be responsible enough to look it up and write it down correctly. But even if you missed it on the second quiz, I posted the solutions to all the quizzes and I wrote it down. These are what lines look like. You guys should have known what lines look like, and you should have known that that's not a line. Okay? You cannot use the excuse, oh, it's been too well. Twice since this semester, I've asked you to do the lines. Right? The general forms. So, that was crazy. Let's see. Right, so some did that mistake. This was there. Some of them get even crazier, actually. Move on to problem 2. Oh, by the way, yeah, some people were giving me, they found the normal vector for the plane, but they didn't plug in the points, so they would write down something like the plane is or something like this, and said that's the tangent. Well, there's an x squared here, and there's a y squared here. If it has a square, it's not a plane. Right? Just by matching up what we know what planes look like. It's a constant times x plus a constant times y plus a constant times z equals some other constant. That's a plane. If you have powers on these guys, it's not a plane anymore. You shouldn't be able to write that down and say that's a plane. It's a really big mistake. Let's see this again. Problem 2, most of you guys got part A correct. You guys did the easy way, not 391 way. So that was good. A lot of people forgot the plus C, took off a point or 2 for that. Part B, the trap, which I told you guys that I would try to catch you, right? Nothing up my sleeves. I told you guys I'm going to put this trap. I said I'm going to give you a vector field, I'm going to let you find the potential function. Right after that, I'm going to ask you to do a line integral. You don't have to do the line integral, it's a trick. Because once there's a potential function, all you have to do is find the final point, evaluate the potential function, minus the evaluation of the initial point in the potential function. I had people trying to parametrize curves, setting up integrals, finding f dot dr. Some people started on the page, couldn't finish, actually turned to the back page to finish up the problem, where I thought I was being nice and giving a bigger hint, so I left a little bit of space to do that problem. Just as a hint to say that you're not supposed to be working hard. Some people didn't get the hint. They fill out all the space, ruin it, so you went to another page at the back and try to finish it. I told you guys that I would do this. I told you this problem is coming up, and I told you how to solve it. I told you this, right? Some people actually got that they should use the fundamental theorem of line integrals, and they actually started evaluating the points. But they actually started doing the intermediate points, right? So, I don't know, I said we had one point, and then we went to another point along one curve, and then to some other point along another curve, and people decided, to apply the fundamental theorem for line integrals to this, and then apply the fundamental theorem for line integrals to that, which is still overkill. I mean, if you did it right, I got the points. I gave you the points, but it still doesn't matter, right? I said to the fundamental theorem of line integrals, the only thing that matters are the endpoints, nothing else. I could start here, go here, go here, go here, run around here, go back here, shoot across over here, come back here. Guess what? The only thing you care about is this and that. Nothing else. Only the endpoints. Okay? It's a potential function. It's independent of path. It doesn't matter what path I take to go from here to here. If this is where I start, that's where I end. I'm going to take the potential function evaluated at that point minus the potential function evaluated at this point. Once you have a potential function, you do not actually do the integral. Yeah, so I catch people with that every semester, and I don't know why, because I tell you guys, right? And I said, put all your pencils down, everyone pay attention. And I made sure you all were listening to me when I said this. I said, I'm going to put this trick on the exam, right? It's not even really a trick, because there were problems like that in the review sheets. Yeah, so I still caught a lot of people with that. Moving on to problem 3. Two things, major problems arose in problem 3. One problem was the fact that people don't know about angles. Okay, so I'm here, right? If I go from here to here, what's the range of angles that I cover?
0 to power 2.
0 to power 2. Okay, what if I go from here to over here?
Power 2 to pi.
What about here?
Power 2 to pi to 3 to power 4.
3 power 2, right? This is 3 power 2 here. 3 power 4 is over here.
Yeah.
All right? And what's this?
3 power 2 to 2 pi.
What about this?
3 power 2 to 2 power 2.
Negative pi over 2 to power 2.
Negative power 2 to power 2. If you went to 3 power 2, you'd have to actually take 2 pi plus another power 2. You'd write it as 5 power 2. You always go from smaller to bigger. That's how you learn to set up angles, right? A lot of people mess this up, right? I'd say something like, they go from here to here, and they tell me it's like 0 to pi over 2, or some of them I went from here to here, and it's like 0 to 3 pi over 4. No, it's not 0 to 3 pi over 4. Mistakes like that, I don't expect you to be making. Another mistake I don't expect you to be making is that when you're doing this problem and the next problem, you ended up having to integrate things like sine squared and cosine squared.
Double angle formula.
So, yes, it's a double angle formula, which I actually worked these guys out in class explicitly this semester as well. So you cannot argue, oh, that was way back in Cal 2. You guys had trouble with this on the quiz and actually wrote it down in class how to integrate these guys. Use the double angle formula, or the half angle formula, they're the same thing. And you split it up, and it's easy to integrate from there. So in the exam, people had to do these two integrals, and what happened? What do you think they did?
They did it wrong.
Guess.
No.
Oh, no, use substitution would actually show some sophistication. They actually, that's right, power rule. They use the power rule on a trig function. What kind of function do you use the power rule for? Polynomials. It has to look like a variable raised to a constant power, right? As long as the power is not -1, you add 1 to the power and divide by the new power. Nope, people did it with the trig function. Of course, there are other people, that's obviously not right. There are other people that know. They're very clever, and they know that, oh, the integral of cosine is sine, so it's actually just this. Yeah, that makes sense, right? The integral of a product is the product of integrals. That definitely makes sense. No. This is not a mistake you should be making at this level. This is not a mistake that people who have gone through Calculus 3 should be making. Right? This is a very serious mistake. Do not take it lightly, you know? There's some mistakes you make in life, and you know, you can sort of brush them off and be like, oh, you know, my bad, or you know, I was young and foolish back then, and no one's gonna judge you harshly. You're like, oh yeah, Jhevon's a good guy. He made that mistake. Just don't worry about it. Just let it slide. And then there are other mistakes that you have no business making, where everyone judges you harshly, and you make them. You should like go off in a wilderness somewhere and separate yourself from society, right? This is such a mistake. You are students who have been through Calc 3. You should know how to integrate this and know that you cannot apply the power rule to a trig function. The first day you did integration in Calculus 1, you learned that. Day 1. Oh yeah, a lot of people actually forgot the second curve. So there was one problem where it was like, I had one curve go around in a circle, and then there was another curve going down here, or something like that. A lot of people did this and didn't do that. Or I think the other one looks like this, and then it ran along here, right? So this is C1, that's C2. You have two curves to worry about. A lot of people just ignore the straight line. They like didn't see it. Even worse than that, a lot of people saw this circle, right? And they wanted to parametrize the circle. Guess how they did it?
R is equal to 1.
Nope, they did. Well, you know, we learned in class that it starts at 1, and they have to figure out what I have to add or subtract to get to this, so it's minus 2t. I had people parameterizing a circle that looked like a straight line. So first of all, they told me in the other part that, oh yeah, straight lines have sine functions in them. And then they come to circles and they're telling me, oh no, they're only linear functions in circles, right? Just to add insult to injury, as if they didn't do me enough damage already. It's a straight line. Linear function. It's not a circle. This does not apply here. We'll get back to that because there was more parameterization stuff later on. So yeah, 4, forgot the second curve. Let's see. There are other arithmetic mistakes like factoring trouble. For example, I think there was a problem where sine squared t minus 1 dt or something like that, right? Now, some students actually did their homework and they realized, oh yeah, okay, so I can write this as 1/2 times 1 minus cosine 2t. But then what they did was they factored out this half, right? And they went like this. Oh, one's cancelled. What's the problem with that? You took a half out of this guy, but not the other guy. You didn't factor properly. If you factor out a half, you would have to put a 2 here. They do not cancel. Factorization, Math 190, Algebra. Okay, let's see here. So in part 4, a lot of people forgot the second curve as well, and also messed up on angles, and also messed up on these integrals. And let's see. So for problem 5, how about problem 5? So I gave you the exact same surface that you saw on your review sheet for one of the problems, fall 2006, I think. Right. So anyone who actually did the review sheet would know right away how to draw that. Right. So the picture that you would have drawn in that problem would look like this. Right. Where this guy is the surface, I think where z equals 1 minus x squared. Okay. But in the test, I didn't ask you to go around all the curves. I actually asked you to intersect in a certain plane. So for example, in one thing, I said, only find the intersection of the surface in the plane y equals 0, in which case you know that this was the curve, right? Right? Because this is the plane y equals 0, so that's the curve. I oriented it so that the final point was in the x-axis, in the xy plane, so it means that the arrow is going here, so that should end up here. Okay. A lot of people miss that, right? So over there they didn't do enough curves. Over here they did too many. A lot of people went over like 4 curves and decided to add the integrals together. No, I actually took it easy on you guys. I actually just do 1 instead of 4. Right? And it gets worse still. So some people were parametrizing this guy, and guess how they parametrized it? That's right, trig functions. That's exactly the, yeah, they use trig functions. X equals cosine z would be 1 minus cosine squared, obviously, right? This hits 1, that hits 1. It's obviously a circle if it is. It curves like this. And what kind of a curve is this? It's a parabola. It's not a circle, right? So either day 1 or 2 of the class, I told you guys about stuff that you're going to have to parametrize it. So it gave you 3 general classes of curves. Circles and ellipses. Ellipses don't show up that often. You have straight lines and pretty much anything else, right? Circles and ellipses you use sine and cosine. Straight lines you use that formula I gave you. Anything else you parametrize in terms of the independent variable. Those are the rules. Right? So basically if you want to parametrize a curve, you just ask yourself 3 questions. Is it a circle? The answer is yes, you use sine and cosine. The answer is no, ask yourself, is it a straight line?
What if it's easier to use
The answer
polar?
is yes, you know what to do. The answer is no, you move on. Well, if it's not a circle or a straight line, then it's something else. You parametrize in terms of the independent variable.
What if it's easier to use polar?
Polar only works with circles. And
Not
with
necessarily.
parametrization. No, this is curved. If you wouldn't use polar, you would use right? So some people said like x equals cosine and then z equals this. No, it's not a straight line. We know this because it's squared. It's not a circle because the z is not squared. So it's something else. And what do? This guy's the independent variable, so you just let that guy be t. Y is obviously the plane that you intersected with, and that's it. Because you're supposed to know what a circle looks like, and you're supposed to know what a straight line looks like, and you're supposed to recognize that this is neither. And it's probably asking a lot based on the first 2 problems that you guys did, but you're supposed to know that. It's not a circle, you don't use sine and cosine. And you don't really know any other way to say it. Yeah. Yeah, so some of these mistakes, as you can see, these aren't like 392 mistakes. These are like calculus, algebra, pre-calculus. And, you know, I was really sad when I was grading for a while because, you know, it was like, I can't believe they're falling for these mistakes, especially when I warned them ahead of time and asked them to review this stuff. And I gave you a review sheet, which I don't think a lot of math professors give review sheets. I thought it would be nice by giving review sheets, being generous to let you know what to expect. But you guys didn't care anyway. Yeah, and you know, I know what students say. You know, Jones Hard gives a lot of homework and blah blah blah, and quiz every day, and so under stress. You know, when I see things like this, I'm thinking I'm not hard enough. I'm thinking I don't give you enough homework. After seeing things like this, I seriously considered giving you Calculus 2 homework along with your 392 homework. I taught Calc 2 once. I was this close to going back to my Calc 2 syllabus and pulling up the whole thing and like assigning every single problem on that syllabus for homework due next week. I was this close to doing it. But 1, that would punish the kids who actually know their Calc 2. 2, if I give more homework, I'd have to grade more homework. So it takes away time for me. Then I thought, oh, maybe I'll just give the kids who did bad Calc 2 homework. But turns out it's actually a lot of you, so it's still a lot of time for me. There are certain mistakes that, you know, you can brush off, but then there are others that you really should be ashamed of yourself. It's not about causing Jhevon grief when making your papers. It's about having some responsibility for what you're doing. First day of this class, I handed out a questionnaire. And what did I see in the major form? Oh, my mechanical engineering major. Electrical engineering major. Oh, I'm civil engineering major. Civil engineering major. And you think it's conscionable that as an engineer you would be making that mistake. You're going to realize in a lot of your engineering classes, they're really just math classes taught by the engineering department. That's all they are. Math classes with a different name. Math is at the core of the stuff you're going to be doing in your career, in your education. It's not something you can let slide, right? It's something you have to take responsibility for. These are one of the tools you're going to use in your livelihood. You're going to use this stuff to make money. You're going to use this stuff to impact the world. You're not allowed to let it slip. You're not allowed to make mistakes like that. What good is a baker who forgot how to knead flour, or a tailor who forgot to stitch two cloths together? What is a surgeon worth who can't remember how to use a scalpel? Nothing. What's an engineer worth who can't do basic calculus? Nothing. I didn't force you guys to be engineers. You chose to be engineers. Take some responsibility for your choices. I shouldn't have to force you to go back and look over this stuff. You should have the responsibility to know, oh, I forgot this stuff from Calc 2 and it's coming up. I should go back and look at it. And I get it. Math slips. I really understand. A lot of people think I don't understand, but I do. They think, you know, Jhevon, you don't get it. You know, you're naturally talented at math. You don't have the same struggles as we mere mortals do. I promise you, I am not naturally talented in math. All the math I can do, I worked pretty damn hard to be able to do it. And I understand that math slip. Back in high school, I did Calc 1 in the spring. Came back in the fall to do Calc 2. Couldn't remember how to differentiate x squared. It's that bad. I literally forgot all of Calc 1 in a summer when I was in high school. I understand. Yeah, you can forget. But I was some kid in high school. I wasn't an engineer. I wasn't an engineering trainee. It's okay for a kid in high school to forget Calc 1. It's not okay for you to forget Calc 1. You're an engineer. It's time to get serious, people. Because some of these stuff I saw in these tests shouldn't see the light of day. It shouldn't happen. Same way that kidnapping shouldn't happen and gun violence shouldn't happen, this shouldn't happen. Same thing. Exactly the same thing. It does not belong in reality for someone to write this down. Someone who claims to be an engineer to write this down. It's a senseless act. It shouldn't happen. It's time to start taking responsibility. And stop there before I start raising my blood pressure. Now, are there any questions on the homework? Yeah. Let's see what problem. They don't have the problem. Yeah.
Oh, it's really long.
Number 10. Right, so probably just do a few. You should be able to figure the rest out on your own.
Yeah. One question. For number 10, would it suffice to say that we can't use some of those for vectors or some of them for scalars? Or do we have to?
No, I'm going to tell you how to do this. So you know that curl, you say curl of f is equal to some other vector, right? So you should know that this guy is a vector, right? And the input is a vector field, right? You can only plug in a vector field into the curl. Same thing for divergence. The input is a vector field. The output is, a partial. It's going to be a scalar, right? So basically that's what you're going to be looking at. So for part A, for example, it says curl of f. That obviously makes no sense because this is not a vector field. So you'd say, no, that doesn't make sense, right? Or div f obviously makes sense. Grad f obviously makes sense. If you look at something like the divergence, this is part E. The divergence of the gradient of f. Right? The gradient of f is a vector field, and then you take the divergence of it, which you can plug in a vector field. In fact, we know what this gives you. It gives you 0. Divergence of some vector field gives you 0. Right? If you take the curl of curl f, for example, that also makes sense because curl f is a vector, and you take a vector and plug it into curl again, so that makes sense.
That's not 0. That's the equation, I think. Divergence. Del squared?
Right, the divergence of the curl is 0.
Oh,
yeah,
right.
yeah. Yeah, you're right. Yeah, so that's basically what it's doing. You're going and seeing that if what you're plugging into these guys are vectors or scalars, and you have to plug in a vector into one of these two, and then depending on their outcome, it determines what you can plug those in. Success. Yeah.
For the gradient, we could take both the gradient of both a vector and a scalar function, right?
No, you won't take the gradient of a scalar function.
No gradient of a scalar function.
There's no.
Well, gradient of a scalar function speaks. Is that feasible? Yeah, it's a function. Yeah.
Yeah, if your f is some function of x,
Yeah, that's
y, then your gradient is the partial.
Would you take the
You gotta-
gradient of
a vector
a
field.
vector?
No,
Yeah.
You can?
You cannot.
no.
I mean, because I saw in the textbook, like, they were doing del squared and it was applicable to a vector field. Like, they did component-wise.
That's a different thing. You don't, here you don't. Were there any other questions? The others were sort of computation.
The interpretation of divergence, if you get a positive number, does it mean that something's flowing out at a faster rate?
Yeah,
And a
like
negative
if
number
you zoom in on a region around that point, things going in come at a slower rate than things going out. Or the magnitude coming in is smaller than the magnitude coming out, then you say it's positive.
Negative is the opposite.
Negative is the opposite. Got it? Okay, in what little time we have left, we're going to start 13.6. Of course, we're not going to finish it. It's actually a pretty long section. And it's about parametrizing.
Question.
Yes.
When do you want the review
Oh.
homework?
By the way, come again?
The review homework, because after this section, there was the other homework for basically the parametrization and the triple integrals. It's like that.
Yeah, that homework next class maybe.
Okay.
but 13.6 won't be due next class because we won't finish it. By the way, I forgot to mention, I wrote "see me" on some of the papers. Basically, anyone who got less than a 70 in the circle, you need to see me, right? Because we need to talk. Okay? Because one, you're going to have to give an account for why you did so bad. Right? One of the problems of the world is there's no accountability. You're going to have to tell me, explain why you did so bad. Second of all, we're going to have to talk about how you can do better moving forward. Because the situation is dire, but it's not without hope. I've seen students come back from some really amazing things. But yeah, if you see me on your paper, or you get less than a 70 in the circle number, you're supposed to see me, and it's not optional. It's mandatory. You have to see me, and we have to talk. If you can't stay at the office hours after a class, then email me and set up an appointment some other time. But we should definitely talk before the second test. Now, I know some of you don't know how to parameterize one-dimensional curves, but now we're going to move on to parameterizing two-dimensional curves, surfaces. Let's see how that goes. So we're skipping the sections in chapter 12, but you're supposed to give me that homework on Wednesday. We're moving on to 13.6, and we're going to learn how to parameterize. So yeah, you really got to catch up on how to parameterize one-dimensional curves, because now it's going to get harder. There are going to be more variables to keep track of. Some of the same general principles apply, and we're going to see that just in a second. So the same way we can parameterize vector curves, we can actually parameterize surfaces, right? So vector curves are just one-dimensional curves in 2 or 3 space. And we're now going to learn how to parameterize two-dimensional surfaces in 3 space, right? So that's what we're going to learn. And we are going to start with a definition. That x, y, z, be continuous functions of so the standard variable to use in one-dimensional curves is t. The standard one to use in two-dimensional curves is u and v. Supposed to look like. You say r of u comma v is equal to these functions x of uv comma y of uv comma z of uv. Is called a parametric surface. equations, x equals x of uv, y equals y of uv, z equals z of uv, called parametric equations. So that's the definition. So a vector curve for a surface, you can distinguish it between a vector curve for a single one-dimensional curve, because for these guys you will have one parameter, only a t. In these guys, you're going to have two variables, right? There's going to be a u and a v. Right? You need two variables to span a two-dimensional surface in 3 space, right? So that's how you're going to be able to tell the difference. So now we're going to talk about what we mean each choice of u, v. Is a vector r of uv, which traces out on the surface. Right, so basically in 3 space what we're going to have is here's x, here's your y, here's your z. So you have this surface hovering around over here. Right? Right? And basically for any uv you're going to get a vector, right? That's going to map to a point, right? This is going to be the vector r of u0, v0, right, for a certain point, and it's going to map to a point on this guy, which is v0, v0 in D, right? Or you can think of it as x of u0, comma y of u0, comma z of u0, right? So for different choices of u0, you get different vectors, and they're all going to give you points along this surface, right? So when you take up all these points and you run over all the values of u and v, you get points in the 3 space. Finish the examples. Maybe I'll just talk a little bit more about that. So, I think we'll probably stop there because the next section I won't finish. But go home and remind.
Yeah, it is.
What do you mean?
This is just like the MATLAB part of 203.
It's a parametric surface.
Yeah, we learned this in calculus 3.
Yeah, I know you learned it in calculus 3. Yeah. You did it in MATLAB. You didn't do everything from this section in Calculus 3. They sort of picked and choose what they told you. But we're going to do the whole section in this class. But yeah, I'm pretty sure you had like a MATLAB on this stuff. And you actually graphed it out. Now we're going to really go into the theory and really understand how these guys work. And we're going to learn how to parametrize surfaces, right? So if I give you a cylinder, you're supposed to be able to tell me what the vector curves that represents that, right? Or a paraboloid, you're supposed to give me the vector function, right? And also we're going to learn about areas in these guys, which we're going to learn about different formulas and another a lot of cool stuff. And just like with one-dimensional curves, they're going to have general categories. You know, if you have a cylinder or anything with a circular trace, you use sine and cosine, and straight lines and planes. Planes, you use something else, etc. So I gotta see. I'm not here.